In this video, we're going to be discussing the nucleophilic substitution reaction, specifically the SN1 reaction and the SN2 reaction. So let's get right into it. So what does nucleophilic substitution even refer to? Well, what it means is that each step of this reaction involves a substitution of one nucleophile, a leaving group, which could be a chloride ion, a bromide ion, it's usually an alkyl halide, on that substrate for another nucleophile. This is the general idea for all nucleophilic substitution reactions and something that you need to keep in mind. The actual mechanism of the reaction differs between the SN1 and SN2, and that's something we'll get into later in this video. So let's begin our study with the SN1 reaction, which refers to a nucleophilic substitution unimolecular. Unimolecular refers to the rate law. This means 1, so in this case 1, which is unimolecular. This means that the rate law only is determined by the concentration of the substrate, not the nucleophile. On the other hand, in the SN2 reaction, which we'll see, the rate law is determined by both the concentration of the substrate and the nucleophile. So that's how they differ. So with both reaction types, the SN1 and the SN2, we're beginning here with the SN1. The SN1 reaction takes place by loss of a leaving group prior to nucleophilic attack. What this means is that there's going to be a carbocation that's formed. This does not occur in the SN2. That's something you need to differentiate between the two. Now in a later video we'll discuss the actual conditions that allow you to differ even further between the two reactions, but when looking at a mechanism, it's important to understand that the SN1 occurs through a carbocation intermediate, whereas the SN2 does not. Alright, so moving along. Prior to nucleophilic attack, prior to it even approaches, the leaving group departs. The carbocation is formed, then the nucleophile can attack, and there you have your product. Now with the ball and stick model, let's take a look at this a little bit more in depth. So we have our chiral substrate. We'll say that this is some alkyl halide. Let's say this is a chlorine atom. It undergoes dissociation, and then we form our carbocation intermediate. From here, we can have one of two things. A nucleophile can attack from this face, or it can attack from this face. This is important because this will determine what stereochemical configuration it has. Will it be R or will it be S in relation to what it was prior? So we had our chiral substrate. Say this is R. It could be S or it could be R still. So it's a 50% chance of it being either of the configurations. And this is known as a racemic mixture, when both can form in equal concentration in a mixture. So that's a pretty solid overview, a clear picture of what this reaction looks like. And before we conclude, one last thing that I wanted to point out is that with any time that we have a carbocation intermediate, there can be alkyl shifts, hydride shifts, so this is something you need to keep in mind. Remember that a carbocation is most stable at that tertiary or secondary, but definitely not primary. So if it's a primary carbocation, it's most likely going to undergo some kind of hydride shift or alkyl shift to enhance the stability of that carbocation intermediate. So moving on, let's do the SN2 reaction. Nucleophilic substitution bimolecular. These go hand in hand. If you've seen the E1, E2 video, or if you've read any of the textbook information about these reactions, the elimination and substitution reactions, they go hand in hand. So the E1 and SN1 refers to a unimolecular rate law. The SN2 and the E2 refers to a bimolecular rate law. What that means is that we're looking at the concentration, of substrate and the concentration, concentration of the substrate and the concentration of the nucleophile when determining the rate law. So they each contribute 1, and therefore that's why it's 2, because they multiply. It is only the substrate concentration for the SN1, so that's why it's just 1. All right, enough with that. So SN2, here we go. Nucleophile attacks and the leaving group leaves. This occurs at the same time. This is known as a concerted mechanism. We'll see this with the Diels-Alder reaction and other paracyclic reactions, but this is very similar in terms of electron movement. So, nucleophile bond forming, bond breaking. It occurs at the same time. This is a concerted mechanism, and this is that intermediate. The product, as the leaving group leaves, the nucleophile forms the new bond, and it is inversion of stereochemistry. In other words, if this is R, the product will be S. Now, there's certain substrates such as a tosylate ion that you can use, and this will conserve the configuration because it's a big bulky substituent, but we'll get into that in a later video. For right now, what you need to know is SN2, inversion of stereochemistry. SN1, it can be either inversion or retention. So let's take a look at a ball and stick model of this SN2 reaction. So we have our chiral substrate. We'll say this is a chloride ion. The bond is forming as the bond is breaking, which we see here, and the new bond forms. So I hope you're getting the picture. Make sure to rewind this and watch it over and over if it needs more time to sink in. But what you need to know is SN1, carbocation, SN2, no carbocation. SN2 is a concerted mechanism which bonds form and bonds break at the same exact time, and there is inversion of stereochemistry. And one last thing, if you want to jot this down, this little list, it's leaving group reactivity. So the best leaving groups are over here, and the worst leaving groups are over here. So here's the main points that I want to point out and I want to leave you with. SN1, no stereochemical inversion. So the reaction runs as follows. Make a good leaving group. The leaving group must depart. The carbocation is formed. The nucleophile then approaches and attacks that carbocation intermediate, and you're left with your product. It can either be retention of stereochemistry or inversion. On the other hand, we have the SN2. There is stereochemical inversion. That's a huge point to grasp. So, the reaction runs as follows. A good leaving group must be present, typically a weak base. The nucleophile attacks upon the opposite face of the molecule of the substrate. The bimolecular transition state is formed, bonds breaking as bonds are forming. The leaving group leaves, the new bond to the nucleophile forms, and then you have stereochemical inversion. So R to S or S to R, either or. So I hope this video helped with allowing you to gain a little bit better understanding of the mechanism of the SN1 and SN2 reaction. If you liked, give it a thumbs up. Leave a comment down below for any videos or any other tutorials that you're looking for. We'll see you guys in the next video.